Hi, my name's Ariana and this is my video lab report for Physics 2211 with Dr. Paducah. This is Lab 1, Constant Velocity. The purpose of this lab was to investigate the motion of an object moving at a constant velocity and compare experimental observations to a computational model. Through this lab, I was able to observe the difference between experiment and theory, where the computational model did not necessarily best represent my experimental findings, demonstrating how this experiment may have outside factors, which we will discuss in the conclusion of this video. Here are some background concepts before we get into the lab. First is Newton's first law, which states, objects at rest stay at rest, and objects in motion stay in motion unless acted upon by a net external force. This helps explain why net force must equal 0 for constant velocity. In the diagrams below, the left image has an applied force that would result in acceleration. This would be when I initially gave the cart a push. However, when the cart reaches a constant speed, assuming there is no air resistance or friction, the forces cancel out as shown by the image in the right, where there is 0 net force. Finally, another important concept is Newton's second law in the form of the momentum principle, which is used to derive the velocity update formula. It is used in the computer model and seen in the next slide. Here are some important formulas that are used in the computer model. The bottom formula was derived from Newton's second law as explained previously, and the derivation is shown on the right. In this experiment, the system was the cart and the surroundings were everything else. I chose the tracker model so that the right x-axis was positive and the left x-axis was negative. I pushed the cart and fell in the center of the track to try and capture constant velocity. I then uploaded the video to Tracker to produce position versus time experimental data, and in this model I assumed there to be no friction or air resistance, in other words, no net force, in order to maintain the idea of constant velocity. Here are the two equations I showed in the introduction slides converted into code. Below are the initial conditions I set in my computer model. I set the cart mass to 0.25 kilograms, but any number would produce the same result, as F net is 0 and therefore mass is cancelled out in the calculations. I set the initial ball position to 0.001 meters in the x direction, as that was the data I received from Tracker, and I calculated the initial velocity from the first tenth of a second, as I determined this amount of time reasonable to estimate initial velocity. Finally, I changed the time step to 1/30th of a second, which is equivalent to one video frame from the Tracker application in order to lend a better comparison. I linked the rest of the code in the slide if you want to take a look at it, but in this section of the code, the formulas mentioned in the introduction are incorporated in a continuous loop that updates the ball's velocity and position according to its previous calculation. Basically, this code predicts the future using initial conditions I provided and 0 net force, and provides the theoretical data later graphed. Here in this graph, both the tracker model and computer model data were plotted against each other. Initially, as you can see, both position graphs have the same slope, and as we know, the slope of a position graph is equivalent to its velocity. But as time increases, the experimental line deviates from the computer model line, and the slope for the experimental line decreases and becomes flatter, indicating a decrease in velocity likely due to a combination of friction and air resistance. This shows that the computer model overpredicted the position as time increases. However, besides outside forces, video quality and tracker human error are possible sources of error, which could also contribute to this deviation. For example, I used the front edge of the cart as my point in tracker, and it was difficult keeping the point consistent in each video frame, and this inconsistency may have resulted in an error. What if the axes were flipped? I explained that I originally chose the right to be positive and the left to be negative in my tracker model. However, if the axes were flipped, the only thing that would change is the sign of the slope of my graphs as shown in the images below. The slopes would be the same in magnitude, just negative, and therefore the conclusions would be the same. The next question is it possible to say what forces are added together to give 0 net force? In the computer model, net force was set equal to 0. However, it is difficult to tell if the net force was 0 in the experiment. While the data suggests there was some outside force, such as friction or air resistance, acting upon the cart, slowing it down, but it is difficult to determine the exact forces and magnitude upon which they acted on the cart. In order to decrease this deviation, this experiment could be improved using an object less prone to frictional forces, or one could try to factor friction in the computational model. Thank you for listening to my video lab report.